Good morning. Let's see, I have time. Thanks for the invite. I really appreciate it. And to have this opportunity to talk about what we've been doing the past few years and why I think it has applications for low resource settings and how it follows this model of open pathogen genomics. So before talking about the work, let's talk a little bit about what open pathogen genomics is. There's this great paper. If you haven't read it, this should be required reading. It should be required in any bioinformatics curriculum. One of the co-authors is here right in the back. But it's 10 recommendations for supporting open pathogen genomics analysis in public health. And it kind of lays out a framework of when you're trying to create this type of infrastructure for public health, what should it look like? What types of considerations should you have? And I've summarized some of the aspects of it, and they're mainly broken into this concept of a data science ecosystem and an environment. And these ecosystems and environments have different aspects of a portal, registry, hubs, workflow management, containerization, et cetera. And what I'd also like to add to this, which was touched upon briefly in the paper when talking about cloud resources, is this kind of resource-limited setting aspect, having low capital investment, low to no cost maintenance, and analysis for support. So I'm going to talk quite a bit this presentation about Terra. I'm not going to talk that much about Theiagen genomics, but what I want you to think about when I talk about Terra or I talk about Theiagen is these are models, not necessities, okay? So you don't have to go out and use Terra, you don't have to use Theiagen genomics, but they represent how if you take these principles from that Nature paper, what can be achieved doing that. And then with Theiagen, we're a team, we have 5 or 6 developers, 3 or 4 trainers working on this Terra project. You can see the impact of what a small team can accomplish with the right resources. And when I talk about resource-limited settings, it's not just LMICs. During the pandemic, a lot of the public health labs in the US could have been considered low resource settings because of their lack of staff, workforce development funds, training, et cetera. Okay, so what is Terra? Just briefly, who made it? Broad Institute, Verily Life Sciences, Microsoft, Google. The Broad Institute hosts Terra. There's a single instance of Terra. It sits on top of Google Cloud. And it's a really neat ecosystem where you have your central environment. And let's see. Nope, that's not going to work. You have your central environment of Terra, but then you have these different aspects of that open pathogen genomics system with the user portals, data repositories, tool repositories, method developers, et cetera. And what's really unique about a system like this is the user portal is kind of separate from the method development. And a user portal provides, kind of like was talked about yesterday in the keynote speaker with Anita, a lot of scientists, they don't want to code. They don't want to work on the command line. They want to be able to have an interface and go in there and work. But the developers want to be able to have complete control, have no black boxes, have all parameters exposed. And Terra is one of those types of things that allows both of those to coexist. And so if you look at this solution of Terra and you look at it with this ecosystem and environment, portal, you're using a Chrome web browser. Registry, we're using DocStore, which is kind of a layer between GitHub and Terra. Pipeline hub, package hub, everything's open source, GitHub, Docker hub. And when you get to the environment, which is more of Terra in the middle, workflow management, you're using the WDL workflow language, which uses the Cromwell engine. Docker containerization, versioning, and auditability and validation are taken through with DocStore, GitHub, and Terra. But most importantly for this talk is in resource-limited settings, everything is layered on top of cloud. And this is a really low capital investment. And later on, I'll show a couple slides on numbers and how it turns high-performance computing into a consumable rather than a capital investment. And a little bit about nonprofit work a little later. So I've just talked about Terra, so why should you even care about Terra? I mean, there's lots of platforms out there. There's many different ways of doing things. Fortunately, when working with the Broad, we have a very close collaboration with the Broad. We have some shared goals, shared aims. And some of the access that we get to Terra, we could look at who is pulling our workflows. So we don't know, or I shouldn't say who's pulling our workflows, how many times our workflows are being pulled. So who's pulling them, what workspace they're going to, that's not available, that's private, that's secure. But we can get counts on, much like you'd at a Docker Hub or something like that, see how many times your container is pulled. We could see how many times the different workflows that we have are being pulled. And that large hump right there is mainly the Omicron wave, like the beginning of, during the height of the pandemic, Omicron, and the blue bars are essentially viral workflows. And you could see after that large surge, we still have steady usage of Terra and the workflows that Theiagen's created. And I've got some numbers here. And so we know that in about 2 years since we heavily started investing in building these workflows, 2 to 3 years, that we've had 5,800,000 workflows used. So that this model of open pathogen genomics, of using cloud, of having this interface, actually works. People use it. What's also encouraging is I broke down these workflow usage so you could see the trends over time. And in the bottom, you could see the blue with the spike in usage of workflows that are specific for viral pathogens, most notably SARS-CoV-2. In green is more the utilities for submitting to NCBI or GISAID, so you could build in workflows to automate those submissions. But what's really interesting is the top 2 panels, where red is the workflows that are specific for bacterial pathogens. So you can see that over time, we're starting to see more and more use for bacterial pathogens, because when we started working with Terra, this wasn't designed to be a solution for the pandemic. This was designed to be a solution for public health bioinformatics infrastructure. And if you look, we have a spike there, probably in around July of 30,000 workflows for bacteria. Maybe that it doesn't seem like a lot, but if you look at the NCBI database, where there was a nice talk yesterday about that, there's only, as of yesterday, 577,000 salmonella and 345,000 E. coli in there. So these are actually really significant numbers. The pandemic has kind of warped our sense, I think, of how many pathogens you should be sequencing. But those are really high numbers. And then the second panel is fungal workflows. So we were heavily involved with the CRS outbreak in the US and Nevada. And a nice thing about an open pathogen genomics framework is you can very rapidly implement new workflows in response to outbreaks. There's a CRS outbreak, there are collaborators, and you could see the number of workflows that were run on fungal pathogens. And you can see some of those spikes are up around 2,000 to 3,000 a month. And I think for CRS and NCBI, there's only about 5,900 references. So this is a significant amount of work compared to what you can see in the public databases. Okay, and so even though we don't know who's using it, we know who we've trained. And since 2021, we've had over 36 trainings, virtual and in-person, genomics, genomic epidemiology, different pathogens, 1,300 participants, 20 US states, 43 countries, asynchronous, et cetera. So you could see the efforts of where the participants were, and actually this week we're officially in South America with a training in Paraguay. So it's really, really quite broad. So why was there such rapid adoption? This gets to the ease of use, compliance ready, and then Google Cloud. And given my time, I'm going to fly through a couple of these slides really quickly and get more towards the infrastructure at the end in the low resource setting. But for those of you that might be interested in Terra, once again, you have a very mature portal of dashboards. You have data-centric tables. You have cards for different workflows. When you pull up a workflow, there are versions. You select the parameters. And if you don't have the workflow that you want in your workspace, you can click on Find Your Workflow, and this gets to that registry aspect of the 10 recommendations. Where you go into Doc Store, you could select an organization. You could see Elwazi is down here as well. You could look at the number of workflows. There's thousands of little workflows. So even though Theiagen has contributed about 150 workflows, there's thousands out there. And you can grab it and very quickly just import it. And you could, Doc Store, you could actually import into multiple different platforms, directly into Terra or Elwazi, but then other platforms support Doc Store. And then you could just import it back into your cards. And so the list of organisms the most analyzed that we, from a lot of the funding has come from the US, from US state public health laboratories. So the priority pathogens in those areas have been along, TB, HAIs, enterics, Legionella, viral pathogens, SARS-CoV-2, obviously, monkeypox, flu, West Nile virus, got flu listed twice, some wastewater surveillance, and then, of course, CORS. But we've also had interest in Vibrio cholera in California and built out workspaces there, for which I've been hearing there's a lot of interest on the African continent right now for Vibrio cholera. So this is one of those things where you could leverage investments from higher resource settings for low resource settings. For the sake of time, you have compliance. In the US, we have FSMA and FedRAMP. You have complete versioning and is available for all your workflows. So if there's a new version, you don't have to switch to it until you're ready. And then you have full audit trails of your job histories. So getting to the infrastructure, which is important for low resource settings, it's cloud native. So right now, Terra is available on Google and also on Azure. The Azure implementation is very different than the Google implementation. So I'm going to talk mainly about the Google implementation. But you have this environment that's instantiated by the Broad, which then fires up resources on the cloud. You have a public health laboratory at the bottom, which logs into that portal, but then you're pulling in all types of resources from other registries. I like to call it also a SaaS with a BYOB, bring your own billing account. So Terra itself is free, open source workflows are free, but all you have to do is find a way of paying Google, which we'll get to in a second. And during the pandemic, it took literally about 90 minutes to get a lot of labs up and running in this type of system. And the nice thing about it being in the cloud is it's very modular. So you could take this base Terra system and expand it with dashboarding and other types of database functionality. And this is an example of some of the work in California, where we've integrated with Google Looker or Tableau or Microbe Trace, NextStrain, and create very mature visualizations. So this is an important slide, I think, and this talks about the feasibility for resource-limited settings. Right before coming out here, literally on the plane, I guess while coming out here, I was downloading some of the workflows that were run in one of our validation workspaces where we test it. And then I was looking at the granular cost breakdown of how much that costs to do. And for 769 analyses, it cost approximately $1,075. And so what you're looking at is if you're a data generator, your cloud compute costs now with this type of model become 1% to 2% of the consumables needed to generate. And that's based on a US dollar value of, say it cost us $100 in reagents and labor, it's going to cost us $1 or $2 per analysis. So this is really attractive. And then also what's really nice is in a resource-limited setting, and it's been very rewarding for us, is that a lot of the work that we've done in high resource settings and funding that we've used from US public health laboratories, these become open source workflows that are available to the community that anybody can use. So in low resource settings, you already have a rich repository of workflows for pathogens that may be of interest. And you have the Docker containerization. Terra is supported by the Broad, so there's no cost there. And then academic collaboration, so we work with a lot of academic groups. So when we have a request for a pathogen of interest, we can very quickly containerize their algorithm, get it into a workflow, get it up on Terra, and somebody could use it. And then there's this nonprofit aspect. So we work a lot with APHL. Gates Foundation invests a lot, not only in this meeting, but in the Broad Institute. But I'm happy to say that we just filed the paperwork for Theiagen Global Health Initiative. And so this is the only marketing I'm going to do, and it's for a nonprofit. It's that we've had, I think, so much success in getting tools implemented in a variety of different environments that we wanted to do this in a nonprofit way, because we've seen some of the struggles in low resource settings is actually getting that the cloud usage set up, getting the accounts to Google or Azure. And if we can start pooling resources and provide just access to that without them having to set up those relationships and then help them with the development of their workflows, that training support and cloud compute, that I think this could be a really viable method for at least starting that sustainability for pathogen genomics in low resource settings. Nothing's perfect. Data management for just about any system needs to be improved. Workflow harmonization, the Broad is working on Nextflow integration into the different versions of Terra, so instead of harmonizing around Docker containerization, we can harmonize around the workflow language as well. Some better tool integration, so if you click a button, you automatically get exported, and my time's up. And then help from nonprofits. So lastly, in acknowledgments, we've gotten a lot of funding. These are some of the major partners in the US between Nevada, APHL, California, Wyoming, Massachusetts. But a lot of collaboration with the Broad Institute, in particular Christine Larth and Danny Park, who's here, funding and assistance and collaboration from CDC, OIMD, EDLB, MDB, all those acronyms from the CDC, Staff B, PHA4GE, and then the highlight here, the bold, are the team members at Theiagen that work most on Terra, and several of them are actually international. James Otieno is from Kenya, Anesh is from Portugal, and Emma and Andrea at the bottom are in the UK. So we're not very US-centric right now, but very internationally focused. So with that, I'll take any questions.